Yes, well, we were discussing about this question in our last class. Due to some interruption, I was to leave this. Okay, fine. You can see this in this question. You have an arrangement where the figure shows this is a pathfinder question. You are aware of this. Shows a part of a large network in which potentials of some of the points are shown. You can see there. You can see here potentials are clearly mentioned 10 volt minus 10 volt. Don't expect that's 0 volt. And we let us assume that this is a VB otherwise. VB. Now the question is, let's see, for whatever may be the reason, as per my observation, see this zone, entire zone is still isolated. Net charge must be 0. Net charge must be 0. If you are not convenient with that, no issues. So, see, C1 times we assume that the potential of this point is X. And let the potential of that point already taken as VB. C1 times X plus 10 plus C2 times X minus VB plus C3 times X minus 10 plus C4 times X minus 0 is equal to 0. I took the point X as a node. Right. You may question me one point that when I am writing this point, is there any current? Honestly speaking, when you said 10 volts is the top drop here. Okay. So I am assuming that the given situation is, practically speaking, I am assuming a steady state, for example. Right. Even then, by solving weight, your C1 value, C2 value, everything is 5 micros. So C has nothing to do in this. Just count X. You have 4X plus 10 minus 10 cancel and minus VB is equal to 0. There are two variables and with the given data, only one equation is possible. So I cannot determine X VB just with this equation. So therefore option B is correct. If the charge on capacitor C2 were also specified, potentials of both the points O and B can be determined. Yes, that's true. Because by knowing that, I will come to know X minus VB independently as one equation. 4X minus VB is equal to 0. Suppose if charge on C2 is given, if given, say as plus Q, for example. So what I can take from this is X minus VB is Q by C2, equation 2. This is equation 1. By solving 1 and 2, I can determine comfortably. So I can take option D also as one of my good option. Right. So if you have any issues on this, you can ask me at the end of this class. Right. Next question from the same pathfinder. Since I am going in an order, Next question. I think 18 is what I have right now. It is also a very standard problem. You are well aware. I think you can comfortably do this also. Well aware of this situation. 18th question. Well aware of this situation. It is a simple RC circuit, not at all a complicated one. Not at all a complicated one. Let me see what options that they have given for this. So you have an arrangement here. What is that? You have is a air filled parallel plate capacitor of capacitance C, which is connected through a resistor R to an ideal voltage source whose EMF is VO. A dielectric plate of dielectric constant K is inserted in the capacitor to occupy very important thing, the whole space between the plates. You are occupying the whole space between the plates. After a steady state is reached, okay, the plate is quickly pulled out. Which of the following is the correct expression for heat generated in the resistance until a steady state is reached? Please try to understand what is happening over here. What is happening over here? That is very important. Here is your battery, resistor, and a capacitor C with dielectric. I'll change the color. The blue color portion is completely filled dielectric part. And hence the charge will be plus Kc minus Kc. Now this one is as same as, I'll just modify the question. This one is as same as a resistor, a capacitor with charge plus Kc minus Kc, Kcv minus Kcv. Right. And you closed the key. That's the question. So what happens after reaching steady state? After reaching steady state, the charge on the capacitor becomes plus Cv minus Cv. Plus Cv minus Cv. What happened actually over here? There is a certain charge transferred. There is a certain charge transferred, delta Q, given by K minus 1 times Cv. This is the charge transferred. And fortunately or unfortunately, this charge is charging the battery. So therefore, work done by battery is minus K minus 1 Cv square. First part of the question is done, but that is not your answer. Initial energy stored is half K Cv square. Final energy stored is half Cv square. Right. Now come back. Work done by battery. Work done by conservative force. Work done by non-conservative force is equal to 0. Now here comes K minus 1 Cv square. We already know work done by conservative force is nothing but initial energy minus final energy, and that is half K minus 1 CV square plus work done by non-conservative force is 0. This allows me to write work done by non-conservative force is minus K minus 1 CV square by 2, boys and girls. Okay, minus K minus 1 CV square. So, right. What is that they were asking? Which of the following is the correct expression for heat generated in the resistance until a steady state is reached again? I think I have done one one simple mistake that 1 minute. I have done one single mistake here. U initial part, I have done a mistake. In fact, the charge on this part is Q square by 2C. U final part is CV square by 2C. So now what will happen here? Till this point, fine, everything is clear. So what is happening is the work done by battery part is minus K minus 1 CV square. And work done by U initial minus U final, which is K square minus 1 by 2 times CV square. And rest work done by non-conservative force is equal to 0. Boys and girls, take CV square as common or CV square by 2 as common. Minus 2Q minus 2 plus K square minus 1. If I am not mistaken, this is the picture. Right. Now write this properly. This one gives you heat. Okay. So by doing which, you will get the condition option, best option part is CV square K minus 1 whole square. Or if you don't believe me, let me substitute this. This is nothing but, as I mentioned, I will take CV square by 2 common. What I am going to get is minus K square. 1 minute. K square minus 2K minus 1 whole square. Minus 1. That is K minus 1 whole square. That's all. I got it. Half CV square K minus 1 whole square by 2 is Pakka correct answer. Right. Trust me, this is the picture. And question number 18. This is a very, very famous model. You are expected to have this question repeatedly, and there is a good chance that this question might be your question for VAT or even in future CUT exams also. So take care to handle this question properly. Now we are moving to the next question. This is my favorite, all-time favorite question. Why? Because some non-ohmic situation is also given. See, in the circuit shown, the device D has the property that if initially non-conducting, it remains a non-conducting until voltage across it rises to a particular value V1, which is less than V0. Boys and girls, right. If then rapidly discharges the capacitor, if then rapidly discharges the capacitor until the voltage across this drops to negligibly small value. That is one important observation. Whereupon it returns to a non-conducting state, the voltage developed across the capacitor is. A very, very, very good question. What is happening initially? You know, an uncharged capacitor behaves like a conductor. You said that the device has a property that if it initially non-conducting, so majorly what will happen is the moment you close the switch, the capacitor keeps charging, which means it is as normal as that of a simple RC circuit. You know the condition for an RC circuit, which is equal to Q naught times 1 minus e to the power of t by tau. Trust me, you can take this till certain value of charge. Right. This is the derivation derived assuming at a certain time t. What is the charge on the capacitor? Accordingly, the potential drop across the capacitor is also V naught 1 minus e to the power of minus t by tau. Sir, what you wish to see? Till the drop across, till the moment the drop across D, which is same as VC, okay, less than V1, because you mentioned in the question, it remains a non-conducting until voltage across it rises to a value V1. Then suddenly it will discharge. It will become zero. The charge across the plates becomes zero. Whereupon it again it reaches a normal stage repeatedly. But so now the issue is the moment drop across D less than V1, D acts as a open switch. A open switch. Yet the instant V across C becomes V1, suddenly charge becomes zero because D acts as closed switch. This is an instantaneous process. Thereafter, again the same process repeated, which means I wish to show you this behavior in a graph. For example, it took t0 seconds to reach a potential drop of V1 across the capacitor. It's a normal graph like this. Now, sudden discharge. It happens at some time t0. Again, to t0. Again, sudden discharge 3t0. And so on. This is x-axis. This is y-axis. And this is voltage representation. And this is V1. Obviously, this is periodic. Obviously, this is periodic. And you may ask me, what is T0? V1 is equal to V0 1 minus e to the power of minus T0 by tau. Boys and girls, V1 minus V0 by V0 is minus e to the power of T0 by tau, or e to the power of minus T0 by tau is V0 minus V1 by V0. And e to the power of T0 by tau is V0 by V0 minus V1. Now, T0 is tau times log E V naught by V naught minus V1. That's the thing. However, don't ask me how is RC, because don't worry about D. So long it is not conducting, it's an open switch. It is an open switch, equivalent time constant is RC. A very good question. I wish such questions you are exposed to, and hence you do well in the BAT examination. Please try to understand, it's a simple mode. Don't ask me what happens if D is in series. Nothing. In lifetime, the capacitor won't get charged. That's all. Next. Now we move on to the next question. This is also a very good question. The comprehension passage. Basically, this is a comprehension passage. See, this time 90% of the questions I have covered in this book. Therefore, you should be alert in doing this. You have a conducting balloon whose radius is A and is charged to a potential V naught and held at a larger height above the Earth's surface so that the charge distribution remain uniform in that. So I see that as a capacitor, that's all right, not more than that. It is attached to a resistance R, fine, no issues. And a valve is open. The gas inside the balloon escapes out through the valve and the size of the balloon decreases. Remember, the radius is decreasing here. The rate of decrease in radius of the balloon is controlled in such a manner that the potential of the balloon remains constant. And this is a very important observation. This will affect the way how I do the problem. Right. Assume electric permittivity of surrounding air equal to that of free space and charge does not leak due to the no corona effect. The time rate at which the radius of the balloon changes is best represented by the expression. My point is, there is an observation, potential of the balloon remains constant. What is the potential of the balloon first of all? The expression for potential at an instant, the charge is a Q. Q by 4 pi epsilon naught R. Now you said potential remains a constant. That's very clearly. The rate of decrease in radius of the balloon is controlled in such a manner. The potential of the balloon remains constant. So clearly Q is 4 pi epsilon naught V into R. Remember, this is initial condition. And again, the right side R is an initial condition. So dq by dt is equal to 4 pi epsilon naught V dr by dt. Remember, dr by dt is minus. So minus dq by dt is equal to 4 pi epsilon naught V minus dr by dt. This is equation 1. So what is actually happening? In fact, it is a discharge. In fact, it is a discharge. Right. How is this possible? I will explain. If you imagine that the arrangement is a capacitor plate whose capacitance changes, and this one is connected to ground, and this is a constant V value, how you will take up in this? It is, this is actually discharging. Please try to understand. Minus, plus, whatever it is. Discharging. Therefore, I into R must be at any point of time that instantaneous charge by C. This is the picture here, by C. I into R is the same as Q by C. That's the picture here. So what is happening basically in this situation is that the rate at which charge is decreasing is so as to uh, provide the sufficient condition that we should remain constant, which means all the time the drop across the resistor is constant. That's what you mean. That's what you mean. So therefore, minus dq by dt times R resistance is V. Now equation 2. So what I have is V by R is 4 pi epsilon naught V minus dr by dt. So which further can be written as minus dr by dt is 1 by 4 pi epsilon naught R. Boys and girls, you have the option, two options were there. One is 4 pi epsilon naught R, the other is minus 1 by 4 pi epsilon naught R. What to answer? Now, 90% of the students, whoever solved till here, don't feel that you are reaching the answer. Read the question properly. Time rate at which radius of the balloon change, they are asking dr by dt, not minus dr by dt. So therefore, dr by dt is minus 1 by 4 pi epsilon naught R. B is the correct answer. Lot of students do mistake here. I'm repeating again. So you should have enough patience to read the full length of the question. Don't take any decision partially on the basis of whatever the information is available. How much heat is dissipated in the resistance R until radius of the balloon becomes half? See, very clear. When radius of the balloon becomes half of the initial value, right? By that time, the charge also becomes half of the initial value because you said Q proportional to R, right? So therefore, see, what was the energy initially? It's like Q square by 2C is the initial energy, right? That is the initial energy, right? Or else you can write this as half capacity C. It is you took this as a sphere 4 pi epsilon naught R V square. What is the final energy? Charge is falling to 1/2. So therefore, 1/4, yes, 1/4. You are taking voltage is constant, half C V square. Voltage is constant. C is reducing to half. Therefore, this is V square 2 pi epsilon naught R square R V square. U final is here R itself becomes 2 and it will become pi epsilon naught R V square. So what is the loss of energy? What is the loss of energy? That's what you need to see. The loss of energy, I repeat, half C V square. Here 1 minute. Radius is R. Okay, what is the loss of energy? So this was the initial energy associated with the balloon, and this is the final energy associated with the balloon. Right. So, by the way, what is the charge transfer? Delta Q. Delta Q. Initially, the charge is 4 pi epsilon naught RV. Now the charge is 4 pi epsilon naught R by 2V, which is 2 pi epsilon naught RV. This is the charge. Right. But this is not mentioned in any part of the question. Why we require not at all. How much heat is dissipated in the resistor? No, clearly, as I mentioned, the drop across this resistor is always constant. So how much charge transferred? Delta Q transferred. So therefore, the entire work is converted to heat, delta Q times V, which is nothing but 2 pi epsilon naught R V square. Here R is the radius of the balloon initially. So very good question. Try to please follow this very carefully. Right. The logic here is the basic logic of this question is this is V potential difference constant throughout. That is the logic of the question. Okay. Right. We'll further move on to the next one. Yeah, this is till now current electricity. You are not exposed to a question of this depth. Till now, in current electricity, you are not exposed to a question of this much depth. A very, 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 very good question, honestly. Right. Now we'll take this question. I think I already pasted this question earlier. Straight away, we'll go to there. Right. Thank you. Consider two electrically neutral concentric conducting thin spherical shells. Hold on. One is this. The other one is this. One is of radius smaller. The other one is of radius 3 smaller. One more important point, you have a point charge plus Q fixed here at a distance 2r from the common center of the shells. The inner shell can be electrically connected to the outer shell through a resistance R1. This is the path. Right. And the outer shell can be connected to ground by means of R2. First part of the question is difficult in this. Remaining part is manageable. How much total heat is dissipated in the resistance R1 after the switch S1 is closed, keeping the switch S2 open until a steady state is reached? I can see three different stages in this. The first stage is I'm assuming the center part as A and the surface point as B and the surface point on the shell as C. And by the way, you have plus Q over here, which is at a distance of 2r. Besides, this is of radius smaller and this is of radius 3 smaller. I require this diagram 3 different times altogether. So I will take 3 different copies of the same. Right. Okay. Thank you. Fortunately, such a pleasure is available in this device. Now let us take initially there is no charge on this. Yes. No charge on this. Net charge 0 otherwise. Not no charge means net charge 0 minus Q plus Q initially. Now, the problem is you connected the inner with outer. There are some intermediate stages. Of course, we go to the final steady state, but we need to every loss, the entire loss is happening in between only. At an intermediate stage, I am assuming some minus Q charge here because charge has to flow from the inner shell to outer shell to make inner and outer same potential. And this part becomes plus Q minus Q. True? Plus Q minus Q? No. Wrong. Not in this way. Minus Q plus Q. I am not cheating you. Please remember. Jitna loss hai, utna gain hai here. Right. And plus Q here. By the way. That's an intermediate stage. And final steady state. That's the final steady state. The final steady state, I am assuming a minus Q naught charge here. And no further current takes place. Minus Q plus Q naught and plus Q. This is the final stage. Please try to understand. In the intermediate stage, at any point of view, VA is the same as VB. And which is, I am speaking only at the intermediate stage. Now, please work. Minus KQ by R due to point charge KQ by 2R due to this KQ by 3R. The net minus Q plus Q effect gives 0. Bias, I am telling you again, this is only in the intermediate stage. During the same stage, if someone asks me VC, when I see picture out, I see that there is only Q charge enclosed by this system. So therefore, KQ by 3R. Remember, all this is intermediate stage. Right. Now I'll change the color. At the final stage, since there is no flow of current between the inner shell and the outer shell, VB is same as VC. Which means by equating these terms, by the way, what is this? K Q by 2R minus 2K Q by 3R. Right. So now you will equate KQ by 2R minus 2KQ naught by 3R is KQ by 3 small r. In this process, you will prove that Q naught is Q by 4. Trust me, I do not have much of space here. Right. A very good move from my side in handling this part. Right. Now the question is, I have a very clear idea right now what charge was transferred between these 2 points. What is heat evolved? At any time, heat evolved is the charge transferred between inner and outer VB minus VC. This is nothing but VB. We already have a clear-cut idea. VB minus VC. Okay. VB minus VC is KQ from the intermediate stage. KQ by 6R 2KQ by 3R times DQ. Q naught. By substituting this, you will get a condition KQ square by R times 1 by 24 minus 1 by 28. This is Q square by 192. Don't forget K is 1 by 4 pi epsilon naught. Pi epsilon naught R. Boys, here is my answer. Right. This is the most difficult part in the entire problem. The first part is the most difficult. Thereafter, what happens? I care nothing. I care nothing for this part. What you call the derivation part of the first part. I mean, the first part, whatever that I have derived, I have nothing to use in the second part. Why? Because when I reach for the second part, what I know is this is the shell of radius 3r with some charge q, and it is ready to take a connection onto the earth through a resistance R. That is what I know for the second part. So therefore, finally, what was the energy available to me initially? Now, please speak only this part. What happened in between, forget about it, because I have already given a proper account for that. UI is 1 by 4 pi epsilon naught Q square by, you already know the energy of the system, Q square by 9R, right? 9R meant 3R. I'm giving an expression for self-formation energy. UI is 1 by 4 pi epsilon naught Q square by 2 times radius. Q square by 24 pi epsilon naught R. Q square by 24 pi epsilon naught R. This is what the energy you have, by the way. Now what happens? The entire energy, whatever it is, so this is going to Earth. This is going through R2 and its entire thing is wasted. So therefore, the proper answer for this is Q square by through. I want heat dissipated in R2 is that what you want? And no heat dissipated through R1, correct. So therefore, answer C. Right? So these are all very good questions, by the way. So I just want to add this part in our notes. Yes, I will immediately share these notes till this point to you all. And please take care of following all these things. A record also will happen very soon, immediately after closing this, right?